Okay, we are going to talk about the one-way ANOVA. So to introduce this, what do you do if you have more than two groups? When we just had two groups, we had a t-test. So in a group, or in a situation where we have more than two groups, we can't use a t-test anymore. So now we have to use what's called a one-way ANOVA. So when we have an ANOVA, we have to have a non-directional research question. This is a case where we can't have a one-tailed or a two-tailed test. It's always a two-tailed. So when examining differences between DBs, when you have more than two levels of an IV, our research question simply asks whether that IV can affect the DB. It is completely non-directional. We can't specify higher because we have more than two groups. But we still have the assumptions of a t-test that we have to have a continuous DB. It must be interval or ratio. If we have a nominal or categorical variable, we can't be running an ANOVA. The other thing we need is a single IV that has more than two levels. So with a t-test, we just had two levels like male or female. In an ANOVA, we might have something like ethnicity, where we're looking at 3 or more. You can look at as many as you want, but I wouldn't recommend more than 3 or 4 because it becomes really complicated. So now let's talk about how we would actually do an ANOVA. Well, the word ANOVA comes from analysis of variance. I don't know why they picked those letters, they just did, probably to make it easy to say. So what we're doing is we are examining variability between different conditions or groups. And that's what we want. We want our groups to be different. But in order to look at this, we also have to consider the variability within each condition. So the people in each group are all going to get different scores. That's going to have a variance within each group. So this is usually called error. This is variance we don't want. We want to look at the variance between groups, not within groups. But ANOVA has to calculate both types to let us know if the differences between groups are bigger than the individual differences within each group. We want to know that our group differences are bigger than the individual differences. So again, we are looking at 3 or more groups. For example, we might have 1 control group and 2 treatment groups. You saw this in some of your scenarios for the last lab. So we might have a categorical variable with 3 or more categories, such as ethnicity, or we might have a continuous variable that we've divided into groups. Maybe we take income and divide it into low, medium, or high income, or ages that we divide into groups, etc. So you can do this with a continuous variable if you divide it into groups. This is also a between group design, just like the independent t-test was. Okay, because it's concerned with the variance between groups. So in other words, are our groups different? Now for a t-test, we had a test statistic that was T. For correlation, it was R. For ANOVA, of course, it's F. The F statistic was named after R.A. Fisher, who was the man who created this statistic. Okay, we saw F's when we studied regression, but now you're going to see where they came from. There are different types of ANOVA. ANOVA is not a single test, rather it's a category of tests. There are many different kinds. The first, the one we're covering today, is the simple ANOVA. This is what's also known as a one-way ANOVA because it only has one independent variable. Okay, so this is a 1 DB, 1 IB situation. It's similar to a t-test, but it has 3 or more groups. The next one is a repeated measures ANOVA. We'll be studying this later. This, again, has more than 2 groups, but it's as though those groups are taking multiple tests over time or multiple measures given to the same participants. It's when you have the same participants in all of your groups. Another one is a factorial ANOVA. This still just has one continuous DB, but now it has multiple IVs, and you're concerned with how the IVs interact with each other. So we're not going to worry about factorial ANOVA this semester. That's something I'll save for 209, something for you to look forward to. So today we're just going to be focused on the simple ANOVA. So this is an example of how a factorial ANOVA would be set up, but again, don't worry about it. I don't want to scare you more than I already have. We're only going to be dealing with simple ANOVAs and repeated measures ANOVA this semester. So if you remember our decision chart before that we used to find when we were doing a t-test, now you see that if we go down our flowchart, we're examining differences between groups, but our participants are not being tested more than once. So we go over to no, and it says how many groups are you dealing with. Now we have more than 2 groups, so it becomes a simple analysis of variance, a simple ANOVA. rather than a t-test. Again, I will get you a copy of this chart. So, hypotheses. What are the hypotheses that go with a one-way ANOVA? Well, the null, as always, is that there's just no difference between the groups. All of my groups are going to essentially be equal. For the research hypothesis, there is a difference between groups. Again, we cannot have a directional hypothesis or a one-tailed test with an ANOVA. Okay, we just have to say there will be a difference. ANOVA will not tell us where the difference is. It will tell us if there is one or isn't one, but it won't tell us which groups were different. Okay? It essentially just tells us if the variance between groups is bigger than the variance within groups. Okay? To find out where that difference lies, we have to do something else, which we will get to in a little bit. So for right now, just know that the F statistic tells us whether or not there is a difference between our groups somewhere. So how do we compute that F statistic? The whole goal of statistics is to explain the variance in our data. We want to know why different people get different results. So remember, in correlation, the effect size was the proportion of variance explained. That's what we want to do. We want to explain variance, and the more we can explain, the better. In a one-way ANOVA, we now have two different types of variance. We have the between group variance. This is if we add up and average all the results within each group, so we find a mean for each of our groups, and then we compare those. We want to see if they're the same, and we hope they're not going to be. We're looking for differences. So the difference between all those averages essentially is the between group variance. It's explained by participants being in different groups. So it's differences based on group. The second type of variance is the within group variance. Within each group, the participants are going to get different results. You can tell how spread out the data is by looking at the standard deviation. The bigger the standard deviation, the bigger the spread of the data. These differences can be caused by any number of things, confounding variables that we're not looking for. So this we kind of consider our error term. In an ANOVA, we're concerned with groups. If the group means are different, we can explain that. It's due to our grouping. The variance within the groups cannot be explained. So you may see these also referred to as explained variance and unexplained variance. So let's say, remember that example where I talked about trees and we're giving fertilizer to trees to see if it works. So this time I have a control group of trees that I'm not giving any fertilizer to, and I have two different types of fertilizer, or maybe different amounts of the same fertilizer. So I divide my trees into three groups: no fertilizer, fertilizer condition 1, and fertilizer condition 2. After a period of time, I measure the height of my trees. In my no fertilizer group, are all my trees going to be the same height? No. Every tree is going to be a little different. What about in either of my experimental groups, the ones that got the fertilizer? Are they all going to be the same height as each other? Of course not. There's variance between these trees. Okay? But the differences between trees in each group are the within group variance. Okay, so every group is going to have trees of different height. We don't know why, because they all have the same fertilizer, so that's my error. That's my within group variance. So now let's say the average height of my control group was 14 feet, condition 1 was 16 feet, and condition 2 was 17 feet. Are my groups the same? Those differences are my between group variance. I can say that a difference between the groups is due to my fertilizer. What are the differences within the groups due to? I don't know. That's my error. That's what I can't explain. So the important equation for ANOVA, again, you're not going to hand calculate anything. I just want you to see where it comes from. Okay? So this is essentially the error that is explained, the between error, or between variance, divided by the unexplained, or the error. Okay? So what happens when the between group difference gets bigger? Between is on the top. When the top of a fraction gets bigger, the number gets bigger. Okay? But what happens if my error gets bigger? It's on the denominator, so whenever that gets bigger, the number as a whole gets smaller. But what happens if they both get bigger together? If they move together, then F doesn't really change. Okay? So we want the within group variance to be small and the between group variance to be large in order to get a large F and to be able to find significance. So the bigger the difference between the between variance and the within variance, the more likely it will be that we'll have a significant result. Just like with all the other tests, you use the value of F and the degrees of freedom in order to determine the probability of that happening. Okay. So if you remember from regression, F has 2 degrees of freedom. The first is the degrees of freedom that goes with the numerator, the between group, and this is just the number of groups minus 1. So k minus 1. If we had 3 groups, our degrees of freedom would be 2. So the first degree of freedom just kind of tells us how many groups we have. The second degree of freedom goes with the denominator. It's the within section. Okay? So this is the number of observations minus the number of groups. Okay? So again, let's say we had 3 groups and we had 100 people. So you would take 100 people minus the 3 groups and you would get 97. And that would be your second degrees of freedom. Don't worry about remembering how to calculate them. SPSS is going to give those to you. But when we report F, we have to report both. So we report F with the degrees of freedom between and the degrees of freedom within. Okay? So for example, we might have F 227. This would mean that we had 3 groups and we had 30 participants. Okay? So the 2 comes from 3 minus 1, and the 27 comes from number of participants in, which was 30, minus 3 groups k. Okay, so 30 minus 3 is 27. Again, don't worry about calculating these. SPSS will give them to you. I just wanted you to kind of know where they came from. SPSS will also give you a total degrees of freedom, which is just n minus 1. That you don't need to report. You just need to report the degrees of freedom between and the degrees within. So that's all I'm going to talk about in this video. In the next video, we'll go through how to do this in SPSS.